are known for their shells. These are the seashells that you're actually going to see down at the beach. Yeah, when you can get there. And seashells are going to be made of the mineral calcite, which is calcium carbonate. So that's the CaCO3 that you see right here. And I'll go to full presentation mode so you can see this a little bigger. There we go. Now, it turns out there are different ways you can stack the calcium carbonate molecules. So one molecule looks like this. You see it's got kind of a big side and a little flat triangular side. And you can pile these up in different ways, and you will end up with different forms of the crystal. So these are just some generic crystal forms. And as you can see, calcite, the normal form of calcite, is when you stack these up and they are in a trigonal sort of form. So there you go. That's what a trigonal crystal looks like. And so they, and they can be clear or cloudy, and they dissolve very slowly in water. So if somebody you know is taking calcium pills, like my parents take these, I think, you want to look at the label and see exactly what kind they're taking. Because if it's from ground up oyster shell, which is ground up calcite, it might as well be, a calcite crystal that they mined up somewhere. That stuff is not going to dissolve very quickly. And so mostly the calcite that they're taking in those pills will just pass right through them and won't actually do any good, make any bones. But there are other forms of calcite that you can get. So aragonite is like the layer you would find on the inside of an oyster. And so this is what a pearl looks like. What you're seeing with aragonite, those sort of, it's like a silvery appearance with sometimes a little rainbow sheen to it. That is actually an interference pattern. So the aragonite crystals are in these little flat sheets, and they're very close to each other, but there's a little gap in between each one. And what you're seeing is the light refracting because of that gap, because it's sort of changing as it passes through that. And so this would be the same explanation for why you're seeing, like when you see gasoline on a puddle. What you've got there is actually two layers. The gasoline layer does not mix with the water layer, and there's a little bit of a gap in between them. And so light refracts off that thing, and as it passes through those layers and some of it bounces back, you're going to get that nice rainbow pattern. So that's kind of neat. So aragonite's another form that seashells make. So they'll make most of the shell typically out of calcite, but occasionally, like the new shell part will be made of aragonite. And there are a few creatures on the planet that can actually make amorphous calcite. This stuff dissolves nice and quickly. There are things other than mollusks that can make a different form, which is called vaterite, which actually consists of several of these crystals together at the same time. It's a really complex thing. Tends to only be made by living creatures, but it is a mineral and it does have a structure. So that's kind of neat. Yeah. And so if you want, you can go look at calcium carbonate there. And to be useful to us, it must dissolve. So I don't know. Shall we go look at this? Let's try it. Oh, okay. So we're going to watch calcium carbonate crystals grow. I knew I put it there for a reason. I just wasn't sure why. So these are little crystal seeds that they put in, like a little tiny bit of a crystal, and just watch them sort of increase with size. The fluid around them is full of calcite, and so there they are, merging together and growing. Yeah, crystallizing. And these are amorphous calcium carbonate crystals that are forming most likely. So I guess that would be non-crystalline, just sort of packed on there, however. And so they dissolve again very easily. All right. So let's knock those out, and we'll get to these guys in a little bit. Back to the presentation. Okay, here's what these crystals look like if you were to see them in the world. So amorphous is just whatever shape it wants to be, but it tends to be in little tiny beads. Aragonite forms needles. Calcite forms little bricks like that are trigonal rather than just rectangular prism or whatever shape you might think. And vaterite is a goofy thing, and this is the one that dissolves extremely quickly in water. And so mollusks have this problem. They're building their shells out of something that can dissolve in water. And so they've actually got to protect their shells from dissolving. Otherwise, yeah, seashells would dissolve because of the ocean. Isn't that weird? So this section is all about how mollusks make their shells. And so we know this best from the common oyster. And so here's the idea, and I'll do a little chalk talk of this in just a second. So at the bottom, in order to make a calcite layer of any sort, in this case we're going to make an Aragonite layer with these little flat crystals like that. So in order to make that, first we have to lay down a flooring, and the flooring is going to be a thing called beta-chitin. Chitin is actually a sugar molecule all joined together. And chitin is going to be the same thing that insect shells are made out of, for example, or crab shells. It's just a nice, hard, durable material, and that's the thing that serves as the base for building up our shell. And then on that base, the mollusk is going to deposit a protein. And we've figured this out for oysters. It's the protein PIF80. And so let's find it here. There we go. That's recombinant PIF80. And so take off the R, and that is the name of the thing. And this is a little time course. So shown here in panel A, this is what happens if you don't put any PIF80 down. You will get some crystallization, but it's going to be this sort of amorphous calcite, just like that, building up just like we saw in that last video. But if you put in PIF80 for in different concentrations, look what it does. So this is the same amount of time. This is 48 hours for each one of these. But look, putting a little PIF80 in there makes a larger formation of calcite. And they're actually laying it down in the Aragonite form of calcite. Shown here, you put a little bit more in, they start to act together, and they make these little sort of areas of flat Aragonite that grow out. And shown here, you put a little bit more in, and yeah, look at them coming together. And so these things will start, each of them will have a little center, and then they'll grow together until they touch each other, and they'll just fill all the remaining space. And so it'll end up looking like little bricks that are all just sort of pushed up against each other. Yeah, just like on a brick sidewalk or a brick wall. And so PIF80's job is to recruit calcium carbonate. It holds on to calcium carbonate, and it stacks it in just the right way to start an Aragonite crystal. So that's pretty neat. Shown down here at the bottom, this is a thing called a Raman Spectrum, where you shoot a laser at these and you'll get certain Raman intensities. And without going into the physics of it, it can be used to identify different materials. So at the top, they're showing that if you had pure calcite, you would expect to see a peak right here, and they're blowing up that peak over here. And you would expect to see a little baby peak right there, and maybe a teeny weeny peak right there. And this is what you see with all of these forms. They're all forming, yeah, it's calcium carbonate in every one of those, so it's not just a salt crystal or something. That tells you that the experiment was looking at what they thought they were looking at. So yeah, PIF80 nucleates. It just starts off the center of each of these little crystals that then fill in until they touch each other and then stop. Now, these things could grow three-dimensionally, and so what the cell does is it's got a layer called the Nucleus Layer. So the mantle is like the muscly part of the actual mollusk. And then the Nucleus Layer is the last layer that they just laid down. So this is the layer of the shell, but this is the shiny part. This is where you would find the part that looks like a pearl still. And the prismatic layer is the part of the Nucleus Layer where there's like a little gap in there. And then underneath that, you got your periostracum, and this is where all of that nice Aragonite has turned to regular calcite. And then on the outside, this brown layer is, sorry, that's the periostracum. The prismatic layer is down here. The periostracum is actually made mostly of protein. So the way that these mollusks protect their shells so they do not dissolve is that they cover them with a protein shell, because protein doesn't dissolve. Proteins are, yeah, some of them are pretty indestructible. And so that's how they do it. That's the idea. So here you're seeing what happens. So in the early time points, you've got your beta chitin floor down here, which is great. And so think like when you're going to lay down carpet in a room, first you put that underflooring or that underlay, whatever you want to call it. That's what the beta chitin is doing. That's forming the surface on which you can build these things. And then randomly, we're just going to seed a certain number of PIF 80s over here. The PIF 80s are going to grow, keep accumulating calcite until they run into each other, and they're going to join up, and it's going to kind of look like, there you go. There's our little brick street, or looks like a honeycomb where it's completely filled in, maybe. And then you need one other protein to make this work, and that protein is going to be from a group that are called Matrons. So here's our Matrons, and here's a couple of their sequences up here. And so you can see Matrons have two consistent features throughout all of them. They have an end, a little tail down here, that has a lot of basic amino acids. And so basic amino acids are going to have a positive charge, and these things could theoretically stick to either the carbonate side of calcium carbonate, or they could theoretically stick to a different protein that's going to be a little bit acidic, have acidic amino acids on it. And then all these little bricks in the middle are going to be repeating units. And the repeating units look like this. So come down here to the bottom, all the yellow repeating units, you're going to have 6 of this, and then 2.57, so I guess we stop right about there of this, and etc. Two of these, 2.14 of those, and these repeats have a lot of the amino acid G, which is glycine, and they have a couple of P's, which is proline. Now, proline puts bends in a protein. So proline, P-R-O-L-I-N-E, is going to put a little, basically a little right turn in the protein wherever you have one of those prolines. And glycine is the smallest amino acid. The side chain is just hydrogen on that, which if you know your amino acids, usually there's a couple carbons down there and something else, but not with glycine. Glycine is basically the amino acid that is just a backbone. And so anywhere that you have a bunch of glycines like this, you're going to have a very flexible region. And so what you see here is something that is flexible in here, and then it's probably going to be rigid right here, and then flexible, then rigid, then flexible, then rigid, then flexible, then rigid, and then it's going to bind to the carbonate side of the calcium carbonate. And so on. These are a bunch of Matrons from different kinds of mollusks. And they've all got this same sort of pattern, the same sort of feature. These guys cluster together and they form a net. So imagine the parts here with all the glycines as forming like the little knots in a net that where you hold the ones that are going across and the ones that are going up and down onto each other. And then, imagine all the white parts as forming the little spacers in the net, like the bit of string that runs from one of these knots to another knot, and so on. So you just imagine a whole bunch of them going up and down and a whole bunch going sideways, and that's its function. So Matron is going to sit on top of all these other things. You'll have beta chitin at the bottom. You'll have PIF 80, which is going to recruit calcium carbonate to it. That'll be the middle layer of our sandwich. And then over the top, we're going to throw a Matron net. And the Matron net is nice and thin, and it just seals off that layer. And so this is how mollusks can control how much their shell grows. They're going to make it in little increments, and when they're done, when it's thick enough, then they throw a Matron sheet over it, and then next time they're ready to grow again, maybe next year, they'll do all of this again. They'll lay down another beta chitin floor, and they'll make some more PIF 80, and once it's grown to an acceptable length, they will throw a Matron coat over the top, and that'll be that. So there you go. That's how the mollusk got its shell. And now let's do that in Chalk Talk format.